Okay. So then the next thing, I'll just double check here. Yeah, what we're going to do is use this Exodus add properties. Brad, this one's not going to work, right? Is that correct? Yeah, it won't work. So, yeah, so I'll do it. I'm cheating. I'm using my own version.
So there was a linking problem in the netcdf Python module that we're fixing.
Yeah.
We're going to make a new release that has all accumulation of all the little fixes we made over the past couple days, all the way by the end of today. It's that Exodus add properties file.
Yeah. So anyway, I'm going to do that in this. Let me make that smaller. Okay. So first, let's see, we'll look at that. Let me just open it up here. Oh. Okay, so here's our script. And what you need here, you need NumPy, which is you'll already have. netcdf4, which you actually do have, but is broken for this script right now. And then spatial data, which you already have from PyLith. So this is our Exodus file that we're bringing in. This is a spatial database that has our shear wave information. And then this is additional information that we're going to use for the sizing function for the to go along with the spatial database. These are just importing spatial data coordinate system. This is stuff for bringing in the spatial database. We have to have all the coordinate system information. Here's our label for it. We're going to do linear interpolation. We open up the database, and then we're going to bring in the data. So, and that's going to be the shear wave velocity. And then all we do is create a cell size function that's the minimum period times the shear wave velocity divided by 10. And then we return that cell size. So we'll call that function down below. Here's the one for our analytical function. And it's just, you're defining the center. This is just going to be distance to this point. This is our distance function, which is just regular Euclidean distance to this point here. And then we have a bias factor, the starting size, and then our function here. So, and then we just create a cell size using this function. We return that. So down here in the main part of the code, there's our Exodus file. We get the coordinates, and then we get our cell size for both the spatial database, that's from the first function we saw, and our cell size from the sizing function. And then we're going to, this is in case we've already done it before. If we haven't already created these fields within the Exodus file, then we'll create them. And so we do that, and then I'm not going to go into huge detail here, so then we just put these variables into the fields within the Exodus file. So to do that, we'll just run that. And so when we did that, we've altered this was our original Exodus output file. We can see what we've done to it. Oh, yeah, that's right. So if we look down here, it's got these two new fields that it didn't have, the cell size dB and the cell size function. So let's just see what they look like. where did it go? Cell size dB. That's our, doesn't look like anything there, but this is vertically varying. So you can see that what we've done is just given a vertically increasing cell size. If we look at the function, then what we've done, we've just made it a function of distance from this point right here. So now we're going to go into Trellis. Let's see, yeah, I already set my directory. We're going to go ahead and open up. We'll do the spatial database one first. So we do the geometry again, and this is the new part here. We've assigned the TET meshing scheme, but now we're going to import the sizing function from this previous mesh that we've added the information to. We're going to tell it that all volumes had a sizing function type of exodus, as well as all surfaces. And curve all scheme stride means that you've made it kind of free to let it do whatever it wants on the surfaces. So we'll go ahead and just do all of that at once. Okay, so now it's imported all of the sizing function information, so we're going to mesh the surfaces first. And what you can see, now we have much higher resolution here, but then on the bottom we have much lower resolution. Okay, we're going to smooth those surfaces just to make sure that they're high quality triangles before we start trying to make tetrahedra. That didn't take long.
You didn't smooth, you just said.
Oh, yeah, right. Okay. Okay, still didn't take long. Okay, then we're going to mesh the volume. Okay. Let's see. So, okay, here's what I was talking about before. Let's see. I don't know if this is going to improve it or not, because I think it's already going to be pretty high quality. Let's look. Okay, well, it's decent quality. It's not phenomenal. So maybe we will benefit from doing some smoothing on this mesh. So here we're using a loop within APRAPRO. And so we start out with a condition number of 2, and then we're going to do 4 loops. And each time we go through, we're going to set it to that condition number, smooth it, and then reduce the target condition number by 0.1. So let's just see how that works. So it'll do 4 loops of smoothing here. Okay, it's actually doing some work this time. Any questions while that's going? It's moving nodes around just to optimize the shapes of the tetrahedra. Yeah, it can. Yeah, so there are other things like the that's why we smooth the surfaces, because then it can, if you give it certain options, it can move the nodes around on the surfaces as well. There are also remeshing commands where it actually will take a chunk and remesh that whole little area. So, okay, let's see how that did. Okay, so that's much better. So this would be a good mesh to use. It's got good condition numbers everywhere. They're all under 2, so that's a pretty good mesh. And then we can export that mesh. Okay, so there's that one. I'm going to go ahead and quickly do the analytical function. We'll just go through. We're going to do the same thing where we get the geometry. We set all of the sizing information right here. Okay. Then we're going to mesh the surface again and then smooth it. I might just do that all at once. Okay. So as you see, we have a graded mesh that's going out from the point that we defined. And then we'll mesh the volume. Okay, so let's check the quality of that. Okay, so yeah, this one could benefit from some smoothing as well. So we'll go ahead and it's doing the same thing. We're going to do it in a loop, reducing the condition number each time. Let's see how that did. Okay, now we have a happy mesh. It got all the way down to what we told it to, so that's pretty good. Yeah, I don't know if we emphasize why it's important to have a high quality mesh, but the better quality the mesh, the faster your convergence is going to be. Some things won't converge at all with a bad mesh. And it's particularly important like near faults, which is typically our problem. If you have poor quality elements on the fault or right there, then you can have a lot of problems, especially if you had like fault friction or something like that. So we want to get our mesh quality as good as we can.
If they're really distorted, the elements become very stiff, and so they can create very local stress concentrations of just a couple cell sizes.
Yeah. So there we go. That's the cell sizing demonstration. So